everyone. The topic we're going to introduce today is interpretation of tumor boundaries by near-2 fluorescence imaging. The experiment result will be combined with 3D stereofluorescent imaging system as the basis of interpreting tumor boundary by incorporating big data and mechanical learning techniques with intraoperative fluorescent imaging system. The critical issue in surgical resection of malignant tumor is to determine the operation scope and depth. In terms of current clinical technology, the standard operation process is tissue sampling for cytopathological staining. However, it lacks immediacy and cannot provide live interpretation results during operation. Since there are no current methods to instantly determine tumor boundary during operation, we hope to develop an imaging system that merges fluorescent imaging with stereoscopic projection, which can assist surgeons by using this method to present tumor area during operation that achieve the purpose of precision medicine. The ultimate goal is to combine endoscope with near-2 fluorescence stereoscopic imaging system through the differences in absorption and permeability of fluorescent imaging agents between benign and malignant tumors. The image can be presented instantly during operation through endoscope lens. By combining mechanical learning and big data analysis, it can determine the characteristics and boundary of the tumor, which surgeons can remove malignant tumors smoothly and accurately. Fluorescence imaging technology has gradually become a novel and promising tool for in vivo visualization. Since it provides real-time subcellular image analysis rates, it can be widely used in biological and medical inspection or clinical treatment. However, fluorescence imaging in the visible region is limited by its penetration depth and background interference from the tissue autofluorescence. It is unable to clearly represent biological complexity of deep tissue. Therefore, near-1 region, also known as near-infrared light region, is considered to be the first window for imaging because it reduces the absorption and scattering of near-IR by blood and water. Near-infrared fluorescence imaging has penetrating power larger than visible light. In fact, fluorescence imaging of near-1 region is limited by interference of tissue autofluorescence as well as photon scattering that affect the image resolution. The result of recent in vivo and mimic experiments shows that if fluorescence imaging is performed with light in near-2 region, it can explore further information at centimeter level and obtain depth resolution at millimeter to micrometer level. The fluorescence imaging quality will surpass fluorescence imaging at near-1 region. In our experiment, we used immunodeficient nude mice, which we inject tumor cell as the subcutaneous layer of the back of the mice. After 5 to 6 weeks, the tumor is formed and has complete angiogenesis throughout. Subsequent imaging experiments can be performed at this time point. In the first step of the experiment, we diluted the aqueous solution of the fluorescent material with zero dilution, then used the fluorescent image to capture its signal to figure out the optimal concentration of fluorescence. Afterwards, we anesthetized our experimental mice with gas, then injected with optimal dose of fluorescent imaging agent through systemic circulation, and then used a raw banded xenon lamp as the excitation light source to illuminate the tumor area, and then capture the fluorescent images through near-2. The system is equipped with a 800 nanometer long path filter for detection, and a fluorescent image for the tumor area can be obtained. Compared with traditional treatment methods, patients are required to wait for a long time for pathological section analysis results before they can continue follow-up operation. However, in the system we developed, we use mechanical learning and big data analysis to establish optimization parameters. We can use this fluorescence stereo production system to allow surgeons to instantly determine benign and malignant tumor as well as the tumor boundaries during operation. We hope that this fluorescence stereo production system, merged with MATLAB platform mechanical learning and big data analysis, can make cancer tumor removal surgery more accurate and personalization to achieve demands of precision medicine.